Hi everyone, welcome to the Ethiopian Space Science Society, the Space Public Lecture Series. This program is jointly brought to you by the Ethiopian Space Science Society and the National Space Society USA Mumbai. We'll have a public lecture. I believe since we have two external participants, let's wait for more people to be let in. So we'll start our event on 3:05 p.m. or 12:05 UTC. Okay, once again, everyone, welcome to our event. This event is brought to you by the Ethiopian Space Science Society and the National Space Society USA Mumbai. This is our Space Public Lecture Series. Each month, we invite professionals from different backgrounds in space science and technology, and then they will get to present their public lecture to the general public. Today, we will have Mr. Prathmesh BARAPATRE. So I will give a brief introduction to Mr. Prathmesh and then we'll continue to the presentation. Prathmesh is a robotics engineer dedicated to advancing the future of space exploration and automation. He is currently pursuing his Masters of Science and Robotics Engineering at Northeastern University, where his work targets complex aerospace challenges like lunar terrain relative localizations and autonomous robotic systems. With over 5 years of engineering experience, Prathmesh brings a deep understanding of next generation aerospace engineering to the stage today. Beyond the lab, he is passionate about science, communicator, and space advocate, serving as the president of the National Space Society USA Mumbai Charter and space ambassador for the National Space Society USA HQ. He has personally mentored over 500 students and also certified gravitational wave science communicator. He is also an alumni of ISU, the International Space University SSP 2024. We are going to look up at the cold, hostile stars and meet humanity's bravest explorers, pioneers who happen to be built from metal, silicon, and pure human curiosity. Here to guide us on this epic 70-year journey from the very first mechanical peep of Sputnik to the self-driving robotics geologists of Mars and flighters of the Titan. Ladies and gentlemen, it's my honor to invite Prathmesh Barapatre to proceed with his public lecture titled We Sent Machines to the Void So Humans Could Fall. Mr. Barapatre, the floor is yours.
Thank you so much, Rialab. I hope you can hear me loud and clear.
We can hear you loud and clear.
Thank you so much for the lovely introduction. And without any further ado, we would like to start with our presentation today. Um, Good evening, good afternoon, good morning for everyone who is joining us today for this talk. I want to begin this like a story. I want to make sure that you enjoy this uh, entire presentation as not just as a presentation, but something like you will take away from today about how things have happened before humans went to moon and before the space era even began. Let's begin by stepping out of our warm homes and looking straight up into the cold, silent stars. Think about the last time you stepped outside on a freezing winter day. You wore a heavy coat, maybe a thick scarf and gloves, because your human body simply cannot handle the cold. Now imagine a place that is hundreds of degrees colder with absolutely no air to breathe and silent invisible radiation cutting through the dark. That beautiful space is deeply physically hostile to human life. We couldn't just jump in. So we did what humans have always done when exploring the unknown. We sent scouts. We built pioneers out of metals and silicons, infused them with the curiosity of human being, and sent them into the void so that one day we could follow. Tonight we aren't talking about cold nuts and bolts. We are talking about the robotic pioneers that took the first punch from the universe on our behalf. My name is Prathmesh, and tonight we are going to look at the mechanical pathfinders that paved the way to our future. To understand these machines, we look at the environment they are thrown into. In as part of our act one of our story, we look at the sentinels, the very first robotic eyes and ears. When you leave Earth's protective atmosphere, you enter a battlefield. The sun is constantly shooting out high speed, high energetic protons. These aren't just warm sun beams that we feel here on Earth. They are microscopic subatomic bullet that smashes through silicons, tearing up the data inside the computer chips. Worse, space is complete vacuum. There is zero air pressure. Do you know what happens to standard machinery, grease, or engine oil in a complete vacuum? It boils away instantly. The lubricants we use to keep gears on the Earth simply vanishes, leaving naked metal gears to weld themselves shut. And these are the actual problems that were faced during our first exploration as we sent machines out there. Our robots had to be designed from scratch to resist these invisible silent forces. On October 4th, 1957, humanity successfully knocked on the door of the universe. This is Sputnik 1. It didn't have cameras, robotic arms, or onboard brain. It was just a polished silver sphere, only 58 centimeter wide, about the size of a basketball, carrying a battery, a radio transmitter, and four whip antennas pointing backwards. Yet, as it orbited our heads, it sent a simple rhythmic beep signal. That simple beep was a cosmic doorbell for us. It didn't carry a complex scientific data as we have known by far, but it announced to the world that we have finally broken through the ceiling of our home world. The space age has officially begun, and it has officially arrived. Having knocked on the door, our next scout went up not just to signal, but to measure the invisible dangers of the vacuum. In 1958, America responded with Explorer 1. This pencil-thin probe carried a scientific instrument designed by Dr. James Van Allen, a simple Geiger counter. Instead of just sending back basic radio pulses, Explorer 1 felt something invisible. It discovered that Earth is cradled inside a giant, highly radioactive magnetic bubble. We call these the Van Allen belt radiation. This discovery has a massive warning sign. It proved that if humans wanted to fly past Earth's orbit to the moon, we would have to design heavy shielding to protect them from these intense magnetic radiation zones. Our mechanical scout the found the trap before we walked into it. Measuring orbit was only the first step. Next, we had to prove a mechanical touchdown on other world without being pulverized on impact. And that was a really big concern back then. By 1966, the race was on to to land on the moon, but landing on the another world is like trying to drop a light bulb onto concrete from second story window. The Soviet Union Luna 9, the Soviet Union's Luna 9 achieved that impossible. It was a gentle thruster guided descent like we see today on Martian missions. Uh, It was a rugged mechanical survival. As it neared the gray lunar dust, it inflated large protective air back, uh, detached its capsule, and bounced violently across the surface. Once it came to a halt, four metal petals popped open like a silver flower, stabilizing the lander on the soil, as it can be seen in the picture here on the side. Once it came to a halt, uh, it then deployed its tiny camera and sent back the first close-up panoramic image of the lunar ground. It proved that we could touch the moon. But even as Luna 9 landed, a terrifying scientific theory threatened to halt our lunar landing plans entirely. In mid 1960s, a prominent scientist named Thomas Gould proposed the lunar quicksand hypothesis. He argued that over billions of years, space rocks have pulverized the moon's surface into deep, fluffy dust as light as sugar powder, like powdered sugar. He warned that if we tried to land a heavy spacecraft with astronaut, it might sink like an anchor in the water or and disappear forever. This was a very valid concern back then, as we did not knew anything about the moon's surface and how dense it is, or if it is actually a quicksand that we are probably getting into. To test this, NASA launched the Surveyor program. The Surveyor 1 was sent on a high-risk direct descent on the moon. It touched down on June 2, 1966. Its three metal-legged, as can be seen in the picture, were packed with strain gauges to measure the impact force. The ground held; it did not sink, and Surveyor 1 became a foot tester, stomping on the lunar ground to make sure the ice wouldn't crack when Neil Armstrong finally took his giant leap 3 years later. As our lunar scout cleared the path to the moon, we turned our sight deeper into space. We 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 started to think to visit Mars and beyond. Before 1965, if you read a science fiction book, Mars was described as a planet of canals, ancient cities, and lush alien forests. We generally hoped uh, to find life next door. Then Mariner 4 executed the first successful flyby of Mars. It captured 22 grainy black and white photos, and those photos delivered a historic reality check. There were no canals, there were no forest, there was only a dry, cratered, frozen, silent desert. Worse, transmitting these 22 photos back to Earth was an agonizingly slow process. The total bandwidth of the probe was only 5.2 megabits, meaning it literally took 8 hours to send a single image. But those slow, grainy images taught us the ultimate truth. Mars is a wilderness. We will have to build homes in if we want to survive. To go even further, our, mech our mechanical scout had to cross the ultimate boundary, the legendary asteroid belt. Now, in 1970s, scientists wanted to send mission to giant outer gas planets, Jupiter and Saturn. But to go there, our probes had to cross the asteroid belt. At the time, sci-fi movies showed the asteroid belt was like a dense, chaotic swarm of spinning rocks, where collision were guaranteed. Many believed no spacecraft could survive this crossing. Pioneer 11 and Pioneer 10 and 11 volunteered to take that punch. They sailed straight to the belt and proved that the average distance between major asteroids is nearly 600,000 miles. The belt wasn't a crowded highway, it was an incredibly vast, simple, empty space. Both pioneers sailed through without a single scratch, showing that the path of the outer planet was wide open.
This is Venera 4. This is Venera 4.
Now, before I start the video, I just want to give a quick go through of what I'm going to show. While America sailed out to the outer giants, the Soviet Union decided to dive into a planetary oven. Well, Venus is a planet of nightmares. Its surface is freakishly hot. It's like hot enough to melt lead over 475 degrees Celsius. And the air pressure is so heavy, it feels like being in a mile deep under the ocean. In December 1970s, Venera 7 became the first spacecraft to land on the Venus and transmit data back. To survive the crushing atmosphere, engineers built Venera 7 with a heavy titanium reinforcement chassis. It plummeted through the thick acid cloud, hit the surface and survived for just 23 minutes before its computer literally melted. But in those 23 minutes, it took the ultimate physical punch, proving Venus was a high temperature volcanic furnace. I want to show you a video that shows how horrifying the temperatures are there. I'm just gonna skip to the middle of
A
the
Soviet
video.
space probe much faster. It was made of a material that would melt at 200 degrees, and so the parachute wouldn't open until the probe was much closer to the surface. Since the pressure on the surface was still unknown, the engineers went overkill with Venera's protection. The walls were 2 times thicker, and the space probe could now withstand a pressure of 180 atmospheres. The Soviets were ready to put Venera 7 through hell. As it hit the atmosphere, the lander slowed all the way down and deployed its parachute. The cord did its thing and allowed the space probe to quickly fall through Venus's thick atmosphere. The probe was now much closer to the surface than any of the previous missions, until, with just 3 kilometers to go, the parachute tore itself apart, and the probe started plummeting to the ground, slamming into the surface at 60 kilometers an hour. The Soviets had another failure on their hands. Or so they thought. A few weeks later, when reviewing the data, they noticed that a very weak signal had actually been transmitting for 23 minutes after the lander hit the surface. As it turned out, the lander actually survived, but it had been knocked onto its side, making the antenna's signal to Earth extremely weak. Incredibly, the last bit of data it sent out showed that the temperature at the surface was a mind-boggling 500 degrees. Since temperature
I don't want to keep going through the entire video. It's a huge video. I've linked all the links to the videos at the end of the slideshow. Now, this wasn't just a single mission to Venus. We also had Venera 13 and 14, which was 12 years later, when Soviet again returned to the Venus, not just to measure the heat, but to record the voice of the hostile world. In 1982, Venera 13 and 14 landed on the Venus. They were only designed to survive for an hour before melting. But before they melted away, they did something very incredible. They deployed microphones and recorded the first ever sound on another world. They proved that Venus has a gentle wind of only 1.5 meters per second. But because this air is 90 times thicker than Earth's, that wind is thick soup that carries massive force, making walking through it feels like resisting a heavy current of water. The Venera probes went so we would know exactly what we are up against. With Venus confirmed as a volcanic furnace, we sent out our most advanced automated labs to search Mars for life. In 1967, NASA's Viking 1 and 2 landers touched down on Mars. These were not simple cameras. They were fully automated biology labs. They carried a long, jointed mechanical scoop that reached out, dug into the red Martian soil, and dropped the dirt inside the testing chambers. Viking executed 3 complex chemical experiments, that is the gas exchange, labeled release, and pyrolytic release. The results were highly confusing. The soil was incredibly reactive chemically, but we found no organic carbon molecules. Viking taught us a major lesson. Finding signs of life is incredibly difficult, and we need far more delicate mobile robotic tools to solve this mystery. While our landers worked on the red surface and sands, 2 orbital travelers launched on a journey that would outlast humanity itself. Launched in 1977, Voyager 1 and 2 took advantage of the rare alignment of the planet that occur once every 175 years. They sent back breathtaking images of Jupiter, Saturn, Uranus, and Neptune. Voyager 1 is the most distant human-made object in existence. Sailing in interstellar space today, they carry the golden record, copper message containing greetings and sounds from the Earth, sailing silently as a message in a portal for everyone who might find it, proving that our robotic scout will outlive the very civilization that built them. By 1980s, we realized that space exploration needed to evolve from simple observation to active physical construction. This brings us to our act two of our story, the extension of man. For the first 30 years of space travel, our robots were most passively observers, static boxes with cameras. But as we entered the era of the space shuttle, we began building machines that acted as extension for human muscles. We began giving our robotic scout arms to grasp, fingers to build, and wheel to drive across alien planes. Right. And our first major construction tool in orbit was a giant mechanical limb that faced a high-stake rescue mission. In 1981, Canada delivered the Canadarm to NASA, a 15-meter robotic limb attached to the Space Shuttle's cargo bay. In 1992, during mission STS-49, the crew was tasked to retrieving a standard 4.5-ton communication satellite called Intelsat 4, as can be seen in the image on the side. The astronaut stood on the end of the Canadarm, trying to capture bar of this spinning satellite, but every time the robotic arm touched the satellite, the light friction nudged the heavy craft away into the dark. After multiple failed attempts, the astronaut executed a daring and unprogrammed plan. 3 astronauts floated out together, grabbed the massive satellite with gloved hand, stopped spinning, and bolted it to the shuttle bay. This historic moment proved that space robotics is not about replacing humans. It's more like a partnership where robotic muscles are guided by human physical intuition. This orbital partnership faced its ultimate trial when we had to perform corrective surgery on our blurry eyes in the sky. When the Hubble Space Telescope launched in 1990, scientists realized with horror that its primary mirror had a tiny microscopic flaw, making all the pictures blurry. Hubble was our eye to the universe, and it was blind. The Space Shuttle crew executed a daring rescue in 1993. Using the Canadarm, they grabbed the massive telescope out of the orbit, docked it inside the cargo bay, and spent days swapping out its cameras and installing corrective lenses. It was robotic precision and human grit working hand in hand. That repair allowed Hubble to look back 13 billion years into cosmic history, proving that with the robotic muscles, we can repair our eyes to the universe. While our orbital limbs built space stations, we finally gave our planetary scouts wheels to roam around another world. On July 4, 1997, a tiny machine named Sojourner rolled down the ramp of Mars Pathfinder lander. Look at this machine on the right. It was literally the size of a kitchen microwave oven and weighted just 11.5 kilogram. It crawled at a maximum speed of just 1 centimeter per second. It had a revolutionary rocker bogie suspension system that allowed its 6 spiky aluminum wheels to climb over the rocky rocks twice its size without tipping over. Now, Sojourner was a toddler taking its first step on alien playground. proving we could actively drive on another planet. With mobile rovers driving on the surface, we also sent a smart orbital scout to search for resources under beneath the dust. Odyssey also became our primary communication relay because Mars is so far away. Small rovers on the ground do not have enough power to beam high definition photos directly back to Earth. Instead, they beam it to the overhead satellite, uh, and Odyssey uses its giant antenna to send that data home. It became the primary orbital bridge connecting Earth and our planetary scout. With water maps secured, we sent two of the most overachieving scouts in human history to find where it once flowed. In 2004, the twin rovers Spirit and Opportunity landed on Mars. They were about the same size of a golf cart and were designed to survive for exactly 90 days. Now, instead, Opportunity survived for nearly 15 years, covering 28 miles across craters and valleys. The engineering team at JPL fell deeply in love with these machines. They treated them like a living teammate, starting every single morning by playing a specific wake-up song in the mission control with the to connect with the robotic partners. They proved beyond a doubt that Mars once had a liquid, drinkable, flowing water. But even the most durable pioneers eventually face an environmental battle they cannot win. In June 2018, a massive planet-wide dust storm blanketed Mars. It turned day into absolute night, blocking 99.8% of the sunlight. For the solar-powered rover like Opportunity, this was a death sentence. Without single day of sunlight, its battery drained, and the internal heaters failed in the freezing Martian cold. Opportunity's final technical data transmission to Earth was translated by a science reporter into seven into seven simple, heartbreaking words. My battery is low and it's getting dark. Grown scientists cried in mission control because that robot wasn't just a piece of metal anymore. It had become a proxy for human presence. Now, before I move ahead, I want to showcase two different landing stages that were used to land these Mars laboratories that we have today on Mars. One video showcases Spirit and Opportunity landing using giant buoyancy airbags, and the other one shows the recent Perseverance landing using skyscraper maneuver.
Atmospheric entry. The radar will lock on the ground in 5 seconds from now. Current altitude 8,000 feet. Moving at a speed of 173 miles per hour, we are near our terminal velocity. At this point in time, we should be on the ground. Stand by.
And these landing systems allowed us to safely touch down Curiosity and Perseverance as our first nuclear-powered robotic geologist. In 2012, Curiosity successfully landed in the Gale crater using the revolutionary skyscraper maneuver, and it weighed around 899 kilograms, literally a size of a small SUV. It doesn't use a solar panels. Instead, it was powered by a nuclear battery that converts the heat of decaying plutonium into electricity. This this means if any dust storm shows up, it can still survive. It carries a very high-tech laser blaster on its mast cam. It can shoot a laser beam at a rock from 20 feet away, vaporizing a tiny spot of stone into a glowing gas, and read the light spectrum to tell scientists exactly what the elements are inside it. And it gave us a laser guided eye to the Mars. As its predecessor, uh, we landed Perseverance, transitioning our scout from simple geologist into active planetary archaeologist. Uh, this brings us to the Act 3 of our story, the pioneers. Now, Perseverance landed in Jezero Crater, an ancient river delta that was once filled with water. Its mission was to drill deep into core Mars samples of the Martian clay, looking for fossilized structures of ancient microbial life. Perseverance has been busy. It has drilled, sealed, and dropped 33 metal samples so far onto the Martian surface at sites, and these tubes are sitting in the red dust right now, waiting for the future robotic delivery pickup to pick them up and bring them back to Earth. We are actively leaving treasures for our future self to find. Now, to help Perseverance find its path, we we brought along the first aerial explorer to take flight on an alien planet, and this was our very first flight on 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 a planet different than our Earth. And ingenuity proved that we can fly in Martian air, which is thin, completing 72 successful flights. This video showcases how the flight actually happened. Um, as the small uh, as a small helicopter transition into uh, exploring distant desert, robotic guardians are protecting human lives right above our heads on the space station. Back in the orbit, we have a Dexter arm, a giant Canadian robotic arm of on the International Space Station. Uh, it it is it, it is used when a high voltage fuse blows or a heavy battery needs replacing outside the station. Astronauts no longer have to risk putting on the spacesuits and stepping into the vacuum uh, where Dexter does the dangerous high voltage electrical work outside, in, controlled by the engineers on the ground, while the human crew sleeps inside safely. Now, there are two more small CubeSats assistants that is currently flowing inside the ISS, and this is where we this is where I bring in the small astrobeam robots. Now, these are the system of three cube-shaped free-flying robots that floats inside the ISS cabin. They use small, quiet fans to fly through the weightlessness environment, as the ISS has environment inside it, pressurized cabins. Um, Astrobi carries cameras and scanners to automatically track inventory, monitor noise levels, and perform daily inspections. By handling this tedious repetitive station keeping chores, these tiny robotic helpers free up the astronauts to focus on groundbreaking science experiments. They are the precursors to the automated robotic assistant that will manage our future lunar and Martian habitats. Now, our robotic pioneers are now preparing to leap far beyond Mars, targeting mysterious ice-covered ocean worlds. This is Europa Clipper, currently flying towards Jupiter icy moon Europa. Europa is covered in a deep sheet of solid water ice, but underneath that frozen crust lies a liquid water ocean containing twice as much as water of Earth's ocean combined. Europa Clipper carries a massive ice-penetrating radar. It flies close to the moon, scanning through the frozen blocks to locate hidden subsurface pockets of liquid water. It is searching to see if an ocean of liquid water kept warmed by the gravity of Jupiter could hold the ingredients of life in the pitch black deep. While we scan through Europa's ice from orbit, another heavy drone is in preparing to fly through the thick organic size of Titan. In 2028, NASA will launch Dragonfly to Saturn's giant moon, Titan. Titan is a bizarre world. It has lakes of liquid methane and an atmosphere 4 times thicker than Earth. Dragonfly is a car-sized 8-rotor helicopter because Titan's gravity is very heavy. Is very low, just 14% of Earth's, and the air is so thick, flying there is incredibly easy. If a human stood on the Titan and strapped cardboard wings to their arms, they could fly through the sky just by flapping. Dragonfly will leap miles at a time across Titan's organic sand dunes, studying the complex chemistry that led to the birth of life. But to support these deep space missions, our robot must first build a refueling station on our closest neighbor. Right now, NASA Artemis program is partnering up with commercial companies to launch a fleet of robotic landers directly on the moon's south pole. These landers carry deep drill systems designed to go into permanently shadowed regions. Those regions that haven't seen sunlight for billions of years, making them colder than deep space. These dark craters hold millions of tons of water ice. Our, our robotic drills will find and mine this ice. Why? Because water can be split into chemically into hydrogen and oxygen to create liquid rocket fuel. The robots are finding this fuel station of the future, so the astronauts can refuel and fly deeper into the solar system. Now, yet some of these ice craters have steep vertical walls that wheels can never climb. To explore them, our robots must leave. How do you get into the crater that is miles deep with vertical cliffs? You don't drive, you hop. This is the concept behind moonfall hopper drones. These are small rocket-powered scouts that are equipped with cold gas thruster. Now, I will let you see the video that demonstrates how it will be done. This is how the story of the Scout ends and how humanity's next giant step begins. So we look into the future years before a human crewed spacecraft leaves the launch pad on Earth. A silent fleet of autonomous machines will arrive on Mars. They will spend years working alone in the dark. They will drill into deep ice to harvest drinking water. They will melt the thin air to manufacture breathable oxygen. They will scoop up the red dirt, mix it up, and 3D print thick, protective radiation-proof walls. When the first human begins finally step foot outside onto the red soil of Mars, they will not only be stepping into the cold, lonely, empty desert, they will turn around, step through an automated airlock, and walk directly into the houses built by robots. This is a demonstration of what will happen in upcoming years. This is more like a small glimpse towards the future of how we are going to build habitat on Mars.
Half a century ago, we had extremely low temperatures. Before any humans set in Phase 1, an ecosystem of 3D printing robots will arrive months in advance of any human explorer. They will construct a protective shield for the base by adopting a modular robotic swarm strategy, a plan that allows for redundancies and enhances the odds for success. Intelligent autonomous robots will have interchangeable roles, from battery storage to scout rovers, logistics to excavational, and even 3D printing units, all integrated with multiple cameras and sensors for navigation. They can reconfigure themselves for a multitude of purposes, ensuring prolonged usage beyond the initial build phases. The smallest configuration is the one-wheeled scout rover that uses ultrasonic scanning to analyze the Martian surface to determine the best regions for obtaining optimum regolith. The digger receives the location coordinates and then excavates the Martian soil. It then delivers the payload to the refining assemblies. Here, large chunks of Martian regolith can be processed down to a finer grain and then delivered to the melter robots in situ. They then use concentrated microwaves to melt the regolith and extrude through the 3D printing nozzle. The shell is autonomously 3D printed layer by layer, over several months by the robotic system. In the next phase, the first astronauts arrive with the habitation units, equipment, and supplies. The robots now take on their second life roles to aid the next phase. They come together to make flexible mobile platforms that can carry the payload from the loading zone to the base. The convoy begins its journey across the Martian surface to the habitat site. The build commences with a connector module placed underneath the protective shield and ready for inflation. The module then unfolds and self-inflates into its final form. The habitation units are then placed into position and sequentially inflated to form the completed pressurized environments. The circular layout of the habitat ensures continuous accessibility of the habitat in the event of a catastrophic failure. Each connector module houses 3 integrated environmental control life support systems, delivering essential services like power, water, data, and oxygen to all the habitation units. A circular conduit delivers these services to multiple endpoints in each pod. The base will be remotely powered by 2 nuclear kilo-power reactors and a solar farm, located a safe distance away from the base. In the next stage, the astronauts will construct and install a flat-pack, rail-based racking system capable of connecting to the distribution system, enabling spaces to reconfigure according to their spatial needs. This modular and radical design principle has been adopted for all the habitat pods, ensuring multi-use, reconfigurable environments. A Martian base should not just be a habitat. It is home for the astronauts. Each pod expresses its own identity, quality, and character. A highly functional design which places the human experience at the core. Spaces include a state-of-the-art research laboratory, a hydroponic greenhouse, a fully equipped workshop with digital fabrication facilities, the sleeping quarters with gym facilities, and immersive virtual reality platform. We believe that the key to success of human habitation on Mars is the health and well-being of its residents. Creating a place where work, life, and living combine holistically to ensure they feel connected to each other, to themselves, and somehow to their distant home.
Our mechanical pioneers have done their part to clear the path. Now the floor is yours. I would like to open up the floor for questions you have.
Okay, thank you, Prathmesh. That was a wonderful presentation. So if anyone has questions, you can raise your hand and then we can unmute you and then you can proceed. So until anyone comes up with a question, I had a question. So maybe as an engineer, what do you think are the absolute hardest technical hurdles when designing these rovers and landers? And looking forward, what role do you see robots playing in the next 10 to 20 years in space exploration?
That's a really good question. Well, according to me, the hardest problem is to solve how we power up our robots and keep them alive for different missions, and as well as make them more flexible, so we don't have the constraint of just sending one specific lab automation that is there on different planets. We can reconfigure them and probably use it for multiple purposes rather than just one specific purpose. If and I do remember that there are multiple researches going on this specific topic where you can reconfigure them for different purposes. Although they are in their very initial stages, there are more things to show up. So, yeah, that's something I would look into the future as well. Can you get back to the second question that you asked? What was the second question?
So the second question is like, looking forward, what role do you see robotics playing in the next 10 to 20 years of space exploration?
Right. Well, right now with missions to moon, getting humans back to moon, we will definitely require human assistance, robots that can assist humans to carry heavy payloads, not just with the rover buggies that will be on the moon to for humans to go around, but more instrumentation that they can carry with themselves without having to offload it from a huge rover, human rover, but also like a side assistant, like a small uh, robotic assistant that can come to you whenever you want, get you the right tools that you need, carry the samples with you. So because the suit is so heavy in outer space that you can barely bend and it is pressurized, it becomes more difficult. Although there is uh, although there is more research happening towards making suits more flexible, making it more comfortable for astronauts to bend down and pick up rocks, but having a robot that can carry stuff for you around, I think that is something I personally look forward to happening.
Okay, thank you very much. Um, Maybe like those of you on YouTube, you guys can also ask your questions. Leave us a comment over there, and then we can forward that. So, I was really fascinated by one of the slides where the Soviet they sent rovers, like I believe it's the Venera mission, and then I think like it's like in 1970s and early 80s maybe. Why do you think that we didn't send additional rovers or like orbiters to Venus? Why is it so hard to explore Venus?
The reason behind why they didn't send it, I don't know exactly why, but Venus is actually like I mean these space missions are quite difficult to come by and difficult to design as well. And I think Venus is catching up with new interest now. There are some mission proposals that I've seen that actually showcases terraforming Venus into making it habitable for Earth as well, or making citizen Venus's sky, making it more habitable for humans to come by. Although we can't go land on the surface, but we can actually live in the atmosphere, right?
Thank you so much. Maybe from my side, like maybe another one. So like in Ethiopia, like there are like a lot of I've seen a hand. I think that Sion, she has a question. You can unmute yourself, Sion, and then you can proceed. Can you hear us? You can unmute and then proceed with your questions. Or you can type your questions on the chat.
Uh, can you hear me now, La'ala?
Yes, we can hear you loud and clear.
Okay. So now we are seeing a lot of the biggest space industries in the world trying to get hold of the South Pole water resources on the moon. And we said earlier we can use the water to fuel rockets. I was wondering if there are any other projects we can do with the resources we get, because we are spending a lot of money on this spacecrafts and rockets. And are there any other projects we can do with the resources we get on the moon?
Right. There are actually multiple projects that are there. It's not just uh, getting those resources for survival, but also looking for minerals on the moon. Moon's dust is actually heavily metal, and there are certain metals that can be used to manufacture stuff on moon. Now, there is this concept called ISRU, which is in situ resource utilization, where you use the resources or the material that is available on that specific area to manufacture things, and that will be how that is how things will go on in near future, where you don't have to get things from Earth to moon. You will start manufacturing stuff directly on the moon itself by using 3D printing technology, additive manufacturing technology, by refining the metals from the moon dust and creating habitats over the time. Although initially we do have to send pressurized modules to stay before we do all those things, but over the time those things will happen.
Okay, thanks so much. I think on YouTube we have a question from Hunter XI60S. And then says, great presentation, Prathmesh. Can you talk a bit more about the proposed refueling station on Moon? Splitting H2O requires energy. How do we make it sustainable and efficient?
Right. Yes, it certainly requires a lot of energy, and we won't be able to do that just with solar panels. So as part of the Artemis proposal, they have made sure to include fission reactors that will power up the moon base, and that will provide us with the necessary energy. Now, because we can't rely on moon's side facing continuously towards the sun, we do have night times on moon, especially on the South Pole. Um, we can't rely 24/7 to have solar light, so we will have to have a sustainable reactor that can provide us power continuously to do this heavy lifting stuff. That's where the entire nuclear reactor concept comes into picture. That's how we'll utilize energy to split this atoms into two different elements, that so we can have hydrogen and oxygen separated out for various purposes.
Thank you so much. I think Lydia has a question. Lydia, you can um, unmute yourself.
Yeah, so when it comes to investment, nations usually require convincing. So, what do you say is the return from space exploration?
I'm sorry, can you repeat that again, or maybe elaborate more on that?
Oh, so can you hear me? Yeah.
Yeah.
So when it comes to space exploration, the government or nations require like compelling reasons to make investments on space. So what do you say is the return from those exploration, especially from planetary explorations?
Um, I don't have the exact answer for what do we how the returns are there, but there's certainly a significant amount of research breakthrough we come across when we started doing space exploration, and there's definitely a returns towards countries towards the countries that have been putting up this huge amount of taxpayers' money into exploring different planets and different moons. Um, if you look back into how the initial missions went during the space race, we had a significant breakthrough in technology uh, for mobile phones. We shrunk down the processor size. Uh, our computational power increased over time, right? I mean, these are some of the examples, but yeah, those are the perks of going for space exploration over time. I hope that answers your question.
Okay, looking if anyone has questions on YouTube or here. I'll give a maximum of 2 chances because we're running out of time. Okay, I think like there's another question on YouTube. So it says lunar regolith is notoriously jagged and abrasive, posing a severe threat of mechanical failure and material fatigue to astronaut spacesuits. What specific degradation mechanisms are most critical, and what current research or engineering solutions are being developed to counter this dust mitigation challenge for long duration missions?
I'm not a spacesuit engineer, sorry, but I do not know the answer for that.
Okay. Yeah, I think like that sums up our question and answer sessions. Um, so we can close our session. So on behalf of the European Space Science Society, I would like to thank Mr. Prathmesh BARAPATRE and then also the National Space Society, USA Mumbai for giving their time and then also with their willingness to give this space lecture possible. So we'd like to thank both the organization and Prathmesh individually. Uh, so we will have the same similar event in the next month. So the Space Public Lecture Series, it's a series by the Space Science Society that will invite different professionals from around the world to talk on their research and then to communicate the space science and technology for the broader public. Hoping to see you all next month. Thank you very much, everyone. And also thank you, Prathmesh.
Thank you, Lialam. Thank you for this opportunity to make this happen, and I look forward to more possible collaborations together.
Likewise. Thank you so much.